Hi, Assalamu alaikum everyone. So in the previous sessions, we have started with the concept of linear regression in that we discussed about the projections. Let me just briefly revise those concepts so as to just brush up these things so that you can understand the upcoming topics in a good manner. The first thing is what we try to find is if we had an x vector for which we wanted to find the projection and it was a let's suppose n cross 1 vector. So in that what we did is we saw that the projection basically was equal to A transpose B minus A of x, that was equal to 0 because we said this is the perpendicular on this AT, or we said AT AX is equal to A transpose of B. This is what we arrived. This is the result that we achieved. So then we said if we want to find this x, so what should we do? We should apply A transpose A inverse on both sides. So that will give us x is equal to A transpose A inverse A transpose B. So this is the value of x. But you know that the projection basically is equal to A times of this x. So the projection we had was equal to A transpose A. This is whole inverse rather. Whole inverse A transpose B. So this was our projection if we want to find the projection. The projection matrix P which we called as that was just this much. A transpose A inverse A transpose. This was our projection matrix. Okay. Let me ask you a few questions so that it's pretty much clear. So then we can go. So let's suppose we have this B. So the equation we had at hand was AX is equal to B. So why did we want to find the projection? Because we saw that this B does not lie in the column space of this A. That's why what we try to do, we try to solve this equation. AT AX bar is equal to A transpose B. So this was basically the equation that we tried to solve. Because we want to find such a B or such a P, for example, we want to find some A X transpose is equal to P. We want to find a P which lies in the column space of A, which lies in this column space of A. So let's suppose if B lies in the column space, if a vector B lies in the column space, what can you say about the projection? So what will be the projection of B then? So what will be the projection of this B? So what do you say? If it lies in the column space, so what should be the projection? So I'm saying what should be P of B. This is the projection matrix we had P. And if you again recall the picture was like this. So we had, let's suppose, some B, some A, and we had a vector B, and we tried to project this B onto this A. Okay, and this projection, this much, this projection was called as X of A. This projection P. So I am saying now, if this B, if this B, this vector, if it lies on this, so what should be the projection then? What should be the projection of B? What can you say about the projection? The thing that we can say about the projection, because it is on the subspace itself, so it must be equal to B. So as you saw in the picture itself, so we had this picture like this. So and we wanted to see if this is some vector, let's suppose A, and we had a vector, let's suppose B. This was our B. So projection was, we tried to draw a perpendicular to this point, and this is what we call as projection, this part. Now what I'm saying is that I'm saying this B itself, so this portion B, itself lies on the line. So this B lies on the line. That means the projection itself is B because it's now in the column space of A. So if you want to show it mathematically, so how can you show it mathematically? You know that projection basically is equal to this. So projection is equal to A into A transpose A whole inverse of A. Okay, and then we have this B. So B basically AX is equal to B. So B we can just substitute this AX. Okay, now you know that this AX is equal to B. So what we can do is, this is transpose. Just see it over here. This is A transpose A inverse, A transpose A. So these two will become identity. So it will again be equal to AX, so which is equal to B. That's what I'm saying. So if the vector B, it lies in the column space of A. If it lies in the column space, then the simple answer, projection will do nothing. It will still be in that subspace only. But if it lies out of that subspace and if you want to project it, then there will be some different value. But if this B lies on that column space of A, then we'll have this B is equal to B only. Projection will be B only. The second thing that I want to show is if B is perpendicular to the column space. If it is perpendicular to column space, what does that mean? That means now we have this. So this is our vector we have, and this is our A. Let's suppose this is our A. Now our B, it is perpendicular. This B is like this now. It's perpendicular onto this. So if you see the projection will be this point. Okay. So this will be PB is equal to 0. If it is perpendicular to the column space. Are these points clear? Just to revise you the things, this was our projection matrix that we got in the previous lecture, and this is some implications which I can show.
Yes, sir.
Nice. So now let's move again on to, we'll go on to the linear regression. Linear regression. Just wanted to see if other people joined. So I think yes, Rian is here, Umar is here. Okay, so we'll go on to this. We have two pictures in hand. Just remember these two pictures. The first picture that we had was this. This was our column space. Let's suppose this is our column space, and then we had our null space of A transpose. This was like this. Let's suppose this was our column space of A, and this was our null space of A transpose. So what we said, our vector B lies onto this like this. So if I'm just claiming, if I'm seeing these two things now, so normally our B will not lie in the column space. So if our B lies in the column space, that means B is somewhere on this column space like this. So if you project this, the projection will be the same. So if it's perpendicular, that means it lies in the null space. Okay, as these two are perpendicular to each other, the column space is perpendicular to null space of A transpose. So if it lies in, if it is perpendicular to column space, that means it is in the null space of A transpose. That's the meaning of this. So normally we'll take the B's like this. It lies somewhere outside the column space, and we want to see its projection. That is the picture I want to show you. That's the first picture, because we will see the linear regression, this program or this algorithm. We'll see it in the two pictures. The first picture will be this column space and null space of A transpose, and we'll also see it graphically. So if you see its projection, so projection will be somewhere like this. For example, this will be its P. Let's suppose this is the P, the projection of this B. Let's suppose this is our B, vector B. We want to project that on the column space. That was the whole point. So then it again has another projection that is on this null space. We have this projection on the null space of A also. So null space of A transpose has this projection. Let's call this E. Okay, so B basically is equal to P plus E if you see it. Okay, so this is the thing that you want to remember. So it has a projection that it can be projected on the column space of A. So that is represented by this P, and we derived the formula for that. It also can be projected on a null space. So null space, basically both of these vectors or both of these subspace are complementary orthogonal, if you remember the previous lecture. So from that we can conclude that this B is basically equal to P plus E. E is this projection onto the null space of A transpose, and this P is the projection onto the column space. Okay, now if you want to find this projection, it's easy. If you want to find this E projection, so this is basically just take identity and minus I multiplied by B, because you know that the projection P, you can just give it PB, so you can just subtract this projection matrix from the identity and you will get the projection, this E projection. Just remember this picture. I'll just leave the space here so I can revisit this picture again. So what is the problem now? The problem that we have to form is called as least squares. So the problem that we want to address is least squares problem. So in that, as I just introduced it previously, let me again introduce it. So we have, let's suppose, data. So in that data, let me give a real world example so you understand it. Let's suppose we have some we have data of people, so in which I have been given two attributes. So for the first thing is age, and then let's suppose height. These are the two features that I have been given. So let's suppose point 1, let's suppose age is 2 and the height is in the meters. Let's suppose 0.5 meter. Okay. Let's suppose age is 3, it's 0.55 meter, something like this. Let's suppose age is 10, it's 1 meter, something like this. So I have been given the data. So what I want to do is, if somebody gives me the age, let's suppose after that we have, let's suppose 20, age 20, it's 1.5 meters. And then you see the maximum height that can be, let's suppose till 25, it is 1.57 meters. Some data is given to me like this. So you know that, let's have this age onto this axis, on the x-axis. And let's have this height onto the y-axis. Okay. So if I want to sort of draw these points, so this is 0.5 height is for the age 2. That's, let's suppose this is age 0, age 1 and 2. Let's suppose this is the age 2. And 0.5, let's suppose this point belongs here. And then this point, let's suppose, belongs somewhere here. Okay. And the 110, let's suppose this belongs, this 10 is, let's suppose, over here. And this belongs here. So there will be some points like this. Some points will be like this. I'm just drawing these points. I just draw these some points. The problem now at hand is, basically I want to fit a curve. Here I want to fit a line basically. So I want to fit a line that's called best fit line. So if I sort of draw it like this is not the best fit though, but it gets the point through that I want to tell you. So this is the line basically which I want to get, so that the error is minimum. So if I, for example, have some other points which I haven't seen the points, let's suppose we have these points, and somebody wants to tell, if somebody gives me the age and tells me, can you give me the height of these people? So I can just extrapolate this. So I can tell, if this is the point, so now the height will be this much. So if this is this is the age given, so this is height. If this point, for this, let's suppose this is the height. This is the problem of least square. This is the problem of linear regression, in which we have been given some data and we try to learn some parameters. So what are the parameters in here? In case of line, we had line is equal to y is equal to mx plus c. So we try to we try to learn this m and we try to learn the c. So there is something called as parameters. So parameters are m and c over here in the case of line. So we try to find the slope of the line and we try to find the intercept of the line. So these are our learning parameters. Okay. So these are the things that we want to learn from the data, and for the other data that will be given to us, we want to predict that by using these parameters like slope and intercept. Is the concept of regression clear now? Why is it called regression? Because now this height can range from, let's suppose, 0 to, let's suppose, 2.5 meters. So there can be any value. So you can have the values in regression. There is no classes. So it will be 0.1, 0.8, 1.3, 1.33, 1.34. So basically this is the problem, a regression problem. Why it's called linear regression? Because now we are trying to sort of draw a linear surface or a linear plane in 2D, or a line in 1D, line in 2D plane, and plane in 3D, and hyperplane, which we call as linear surfaces. We draw this linear surfaces so as to fit this to the data, and we try to predict this. Is the problem of least squares, or is the problem of linear regression clear? What we want to do, and this is basically called a statistical linear regression. We are trying to do it statistically. Is it clear?
Sir,
Yeah, please speak because I cannot see the screen though. So you have to speak. So this is the problem we want to see. So basically everything boils down to the equations now. If you see this is our intercept m and c. Let's represent them with c and d or something like that. So let me give you a real example now. Let me give you some example which I'll just apply the regression on. So let's suppose we have 3 points have been given. We have a point 1 1 in which we have x and y. Let's suppose these are c and d. This is our point 1 1 1. Let's suppose some other point is 2 comma 2, and some other point, let's suppose, is 3 comma 2. So these are 3 points that are given. Okay, these are 3 points. So let's suppose we'll draw these 3 points. So let's say this is 1, draw it clearly. Let's say this is our 1, say this is 2, so this is 3. Again, this is 1, this is 2, and this is 3. Let me draw these points with the red. So 1 1 is this point. If you see, this is the 1 1 point. 2 2 is this point. 3, 2 is this point. So what I want to see, I basically want to predict a line. I want to sort of fit a line, which is like this. Okay, this is the line I want to fit because because these 3 points are not collinear. Collinear means they are not on the same line. So I'll have to draw a line in such a way so that the error is minimized. So now what I will do is I'll project this point. This point will be projected onto this. So here is the projection of this point, and here is the projection of this point, and here is the projection of this point. So these white dots are projections. So these are projections. Okay, and this red crosses, they are the real points. Okay, now there will be some error. So here this is the error here, so here this is the error, and here this is the error. So this line represents the error. Okay, so now we want to fit this line such that this error is minimized. Okay, so the problem here is we want to fit this line so that this error is minimized. So the whole point is now how to make this error minimized. So if you have to form an optimization problem of this, let's suppose this is y and x. So let's suppose this is t. Let's call this t. Let's call this x is y axis. So here now we have we have to find y is equal c plus dt. The learning parameters here are this d and this c. As we had this y is equal to mx plus c, I just represent this with cd. These unknowns are cd. So if you represent this equation, the first equation, if you represent the first equation, this one point, this point, if you want to represent it algebraically, so how can we represent this? So this basically says c plus dt is equal to 1. So what's the value of that? C plus d, basically t is equal to 1. C plus d is equal to 1. That's the first point. C plus d is equal to 1. This is the representation of this point. What's the representation of second point? That means c plus 2d is equal to this point. This point is represented like this. C plus 2d is equal to 2. Then what's the representation of third point? That is c plus 3d is equal to. This is not d, sorry. This is 2. So these are the equations of 3 points. If you see, how do we represent this? And this is the generic equation. This is the equation of line that we want to fit. Now clearly you can see that if you take a matrix out of this, so the matrix A matrix will be 1 1 1 1 2 3, and X matrix will be CD, and our B will be 1 2 2. This is our A, this is our X, this is equal to B. So are you see the process how I'm trying to first give you a real world problem, then I'm trying to mathematically model it, and then I'll apply the mathematical techniques that we have learned so far. Is it following?
Sir.
Is it following from discussion?
Yes, sir.
So what I had is I had given 3 points. So my job is now to fit a line onto that. So this is just in 2D. So we have given 2 points. We have given 3 points, and in which these points belong to R2 basically. So these points belong to R2. So what I'm saying is from the first point I can write this equation c plus d is equal to 1. Now from the second point I can write this c plus 2d is equal to 2. And from the third point I can write c plus 3d is equal to 2. Now you clearly know that this 1 2 2, it is not in the column space of, it does not belong to the column space of A. Clearly you can see that, because now you see this equation is saying c plus 2d is equal to, this equation is saying c plus 3d equal to. So you clearly see that there cannot be values for d and c for which both of these equations are equal. So this is some sort of contradiction. So I'm saying c plus 2d is equal to, then the next moment I'm saying c plus 3d is equal to. So this is contradiction. So from this it's clear that this vector 1 2 2 vector, the b vector, this does not lie in the column space of A. So now what's our problem? So the problem is we have to find a nearest vector. We have to find a nearest vector which will be in the column space of this A. So I want to find the nearest vectors to these. I want to find the nearest vector to this B, so that which lies in the column space of this. That is my problem now. Okay, if you again remember the projection, so what we try to do in that is we had this A transpose A x hat is equal to some A transpose B. This is what we will solve. Okay, this is from the projections. If you see, so then we had to find this x hat and we'll find the projection. So now I'll solve this equation and I'll get the value of C and D. Okay, and I'll get, this is basically this A transpose B is the nearest P. This is that point P which is nearest. And what is the problem that we have? We want to minimize these errors, the errors that we have. Let's suppose this error is E1, the first point's error is E1, the second point's error is E2, and the third point's error is E3. So we want to minimize these errors. So how to minimize the error? Let's say we'll have E1 is basically equal to, so whatever we'll do, that is ax minus b. This should have been equal to 0 basically, but what we try to do is we have to minimize this. So we'll get it as minimize. So we'll not just minimize minimize them at minimize just the value. So we'll just square it. So as if some value is negative, so we'll make that positive. So this squaring has a different meaning as well. So whatever background you have for now, just take it that we don't want to just have the negative and positive value. We'll just get all the values as positive. So this is the error one. So error one square basically is this one. So this is what should be minimized. So this is x1 point, okay, x1 and b1. And error 2 basically is error 2 square is that same a x2 minus b2 whole square. And error 3 square is a x3 minus b3 whole square. So this is what we have. So we have to minimize this. So our error was ax minus b is equal to e is the error, and squared error is you have to square this. This is a squared error. Now, in order to formulate this mathematically, what we write is we'll write something like this. We have to find values for this x hat, for this c and d, such that these errors get minimized. The sum of these errors get minimized. So I want to minimize these errors e1, e2, and e3. This is my job mathematically. If you ask me, what's the job? My job is to minimize these errors. Okay. So it can be solved in different ways. One way to solve it is using algebra. One way to solve it is using the differential equation, using the optimization calculus basically. So what I will do is I'll first solve it mathematically by using the algebra that you had, that you learned. After that, maybe we'll go to the optimizations as well. Just I'll give you how to solve it by the optimization. Now this is the equation that I had to solve. Now clearly you saw that this b does not belong to the column space. Now what I told you is that we'll find the nearest b such that the error is minimized. We'll find the nearest b such that this e1, e2, e3 is minimized. This should be minimized. So now what I'll do is I'll solve this equation instead. I'll solve this A transpose A x hat is equal to A transpose B. Let's solve that. So now our job is find, that's x hat, that's our C and D. Okay, we have to find C and D and that point P, P at the projection, such that this A transpose A x hat is equal to A transpose B. This is our job that we want to find. Okay. Again, let's first solve this part, A transpose A. So what is that? Because we know that A is equal to 1 1. A is equal to, if I write it here, so A is equal to 1 1 1 and the other is 1 2 3. This is our A. So now let's first find this A transpose A. This is equal to 1 1 1 1 2 3. Now transpose of this, so this is our A and A transpose. So this is what we solve. So now in order to multiply this, so this is now 1 1 1 2 1 3. This is what I have to find first. So I am finding this portion. Okay. And now I'll compute that. So if I have to compute this, so this will be 1 square, this will be 1, 2, this will be 3. Okay. So then 1, 1, then 2, 3, this will be 3, 2, 5, 6. This entry will be 6. Just cross check my calculations if they are right or wrong. And as you know that ATA is a symmetric matrix, so I guarantee know that this will be 6 here. So now I have to calculate the last entry. That's 1 square plus 2 square, that's 4, 5, 9, that's 14. Okay, so this is the matrix that I got. The A transpose A is equal to this. Okay, now I again will compute this A transpose B. So I'll compute this A transpose B. So now what I can do is I'll just take this A transpose, the A transpose B part. That is 1 1 1 1 2 3. And what is our B? Our B was, if you see it here, so B was 1 1 2. B was 1 1 2. So that is equal to, this B basically is equal to 1 1 1. So the first entry will be 1 plus 1 plus 1, that is 4. This will be the first entry. It will 4. Now it will be 5. 1 1 is 1, 1 is 1, 2 plus 3 is 5. So this will be 5. So then what will the second entry? So this will be 1 square plus 2, that's 3, 3, 6. So this will be 11. So now we have solved this A transpose and now we'll put the value. So what I'm saying you is that this 3, 6, 6, 14 multiplied by CD, this basically is equal to 5, 11. That's what we got out of this equation. A transpose A x bar is equal to, if you now write this in the equation form, if you write this equation form, so this will be 3c plus 6d is equal to 5. Okay, 6d 6c plus 14d is equal to 11. These are the two equations now we'll solve. I'll find c and d now. We have to find the c and d. Now you can just use elimination or whatever the methods that you have been taught so far, and we can do that. Okay, let's find that. So how to do this? So we'll just multiply the upper equation with 2. So we'll get, multiplying this equation with 2, so we'll get 6c plus 12d is equal to 5. Okay, and then we have 6c plus 14d is equal to 11. So now we'll negate this, negate, negate, and negate. This will cancel. So this is minus 2d is equal to minus how much? 6. Yes. So this will be d is equal to I think 3. Is d is equal to 3? Just check my calculations because I'm really skeptical of the calculations. This should be, is it 6 though? Just check it once. I don't think this d should be equal to 6. Let me again do it. So this is 6, 2 is 12, 3, 6. Oh, this should be 15, sorry. That's what I, so this basically is now 4. Is it 4? Yes, it should be 4. Hmm. Still, I'm skeptic about this. Yet check it. This is 10, not 4. 10, 10, 10. Sorry. Are you guys here? Because they just check the calculations. I'm making mistakes and you are not able to identify the mistake. This is 2, 5 are 10. So I have to write 10 over here. So this is 1, minus 1, minus 2, and minus minus cancel. D is equal to 1 by 2. Okay. Is it clear? Is it clear how I got D is equal to 1 by 2?
Yes, sir.
First tell me, are you guys here? Because I was making mistakes and you are not able to catch the mistakes. Rian, are you here?
Yes, sir.
So just please keep
Hello.
the track of
Yes, sir.
calculations. So now D is equal to, I'll just put this D in this. So this will be 3C plus 3D is equal to 5. So 3C plus 3, that's equal to C is equal to 2 or 3. Just check the calculations. I think C is equal to this and D is equal to this. Now we got these parameters. These are the parameters we wanted to find. The C and D. So they are the parameters I wanted to find. Now I found the parameters. Okay. So if these parameters are found, now what I can say you that is that this, the equation that I wrote, that equation, if you see it here, that was y is equal to c plus dt. Y is equal to c plus dt. So now I have the equation y is equal to 2 by 3 plus 1 by 2t. This is the line that will be given by this. So this is the line that we have. Is it clear how I tried to follow the how I did the calculations and I tried to find the equation? Now what I want to do is I want to find the projections. So I want to find the projection of all the points. So what will be that p? What will be that p? For p1, p2, and p3. So where will these things get projected? So what I'll do, I'll just substitute in these equations. So I had these 3 points. I have 1, 1. I had 2, 2, and I had 3, 2, I guess. So these were my 3 points. So now what I will do is, so I'll have to see where will what is the value of y if given the value of t. So I'll have to find those values. So just if you see p1, p2, and p3, I have to find where will they fall on this line. So this is my t. So this value is t. I'm keeping this value 1, 2, 3 as they are. This 1, 2, 3 values. I want to see what is the value of y. What is the value of y that I'll get? So y. So the first 2 by 3 plus 1 by 2 multiplied by 1. This is the first thing, that this is our t and this is our y. Now I want to see what is the value of y. What's the projection onto that? So this is if I'm not wrong 7 by 6. Can you calculate it? So it will be, discover, this will be 2 to 4, 4 plus 3, 7 divided by 6, yes. So if I have to calculate for 2, so that is 2 by 3 plus 1 by 2, and then the value of t is again 2. So this will be 2 by 2 is 1, so this will be 2 by 3 plus 1, that is equal to 5 by 3, if I'm correct. This is 5 by 3. Okay, what is the value of p3? 2 by 3 plus 1 by 2 and 3. So that will be 3 by 2. This will be 2 by 3 plus 3 by 2. So that's 4, 6 is 10, 10 by 6. This is 10 by 6 if you see it. This is 10 by 6. So these are the points. So if you see this figure, these projections are the values we got. We got 7 by 6 and I got 5 by 3 and 10 by 6. So these are the values I got for these points that I just marked with the white on these projections. Now you know that if I want to find the error, this E1, E2, and E3, E1, E2, and E3. If I want to find this, so what I will do is I'll just subtract this. So if you see, I told you that the vector B in total, that was equal to P plus E. Okay, so vector B had 3 entries. This P now has 3 entries. Now if I want to get this E, so E will be equal to B minus P. Okay, and I want to find the errors. So errors will be error vectors. So E1, E2, and E3. So what will be the value of these errors? So what is the value of first point of the B? The first point of B is, if you see, this 1, 2, and 2. So you'll have to see 1 minus 7 by 6. Then the second point will be 1 minus 5 by 3, if I'm right. Yes. So then third point will be, this is 2 minus, sorry, this is 2 minus 5 by 3. And this is 2 minus 10 by 6. Okay, so what's the value of this? This is 6 minus 7. This is minus 1 over 6. This is 6 minus 5. This is again minus 1 over 3. Okay, and this error here is 6 to 12, 10. This is 2 by 6. Okay, are you clear with this?
Yes,
And
sir.
one will be 1 by 3.
Which one?
E2, E2.
It's okay. Yeah, I think this is 1 by 3. Okay, so here you will see this is 3 to the 6 minus 5. I think calculations are okay. 6 to the 12 minus 10. I think these are okay. The calculations are okay.
Okay.
Is it? So just check it once. Can you just confirm? I think this should be 2 by 6 then. This is 3 minus 5, but this is 2 by 6. Sorry. So is it 2 by 6 even? This is the first is 1 by 6. The other, I have written it somewhere, but I cannot find that exactly. So this is 5 by 3 and 10 by 6. Have we done these calculations correctly if you see this? I think this is a 9, this is 9, this is 13 by 6. That's why I want to just say, because I'll get these calculations wrong because I have to see. Just keep a view on my calculation so that these are not wrong, because I want to get the answers at the end. So this is like this. This is 2 to 4. 4 plus 9 is 13 by 6. Huh? So now this is, I think, accurate. This was our 1 by 3. So this is 1 by 3. This is minus 1 by 3. This is 1 by 6. Sorry. So this is okay. And then if you see this, so this now is not 5 by 3. This is 5 by 3. 2 to the 4. This one. 2 to the 4 plus 3 to the 6. This is 10 by 6. If you see this one, this is 10 by 6. This is 2 to the 4. 3 ones are 3. 3 2 is, this is 2. 3 to the 6. So 4 plus 6 divided by 6. So this is 10 by 6. This one. If I have to do it like thoroughly now. So I was hoping that somebody will catch the mistakes, but I think you are not in the present in the class. You are somewhere else. This is 2 to the 4 plus 3 to the 9 divided by 3 to the 6. So this is 13 by 6. Yes. So these are the things that I got. Now this is 1 minus 7 by 6, and this is 2 minus 10 by 6, and this is 2 minus 13 by 6. Okay, this is 6 to the 12 minus, this is minus 2 over 6. Okay, and this is 6 to the 12 minus 1. This is 1 by 6. Okay, so these are the errors. Yeah, I think this is accurate now. So these are errors that we got. Now we have two things. So we had this we had this initial B that was equal to P plus E. So this B initially was 1, 2, 2, if you see that. The projections of this B onto that line, y is equal to mx plus c, that was 7 by 6, 10 by 6, and 13 by 6. 7 by 6 and 10 by 6 and then 13 by 6.
Sir, I think value of E2 is wrong.
Value of which? E2
Yes, sir. Sir, it would be 2 by
plus.
6.
Will it be plus?
Yes, sir.
Okay, nice. Nice, nice, nice. Then we have this plus E. So what is E? E is minus 1 over 6. This is 2 by 6, and this is 1 by 6. I have to keep a track of different things. That's why I can make mistakes in the calculation. So please be in the class so that you detect these mistakes. So this is our B,
E3.
this is our P, and this is 13
Sir,
by
E3 would
6.
be minus 1 by 6.
E3 is minus 1 by 6.
Minus
Nice.
1 by 6. Yeah.
E3 is minus 1 by 6. That's what I wanted from you guys. So yeah, you just calculate these things. So now if you see these, 7 by 6 minus 1 by 6, this is equal to 1. So that's how we calculate it. Now the best picture. I have two pictures in hand. I told you that you have to remember two pictures. This is the first picture in hand that we have. This is the first picture in hand. Okay, and this is the second picture that you have to remember. Now this P and E, they should be perpendicular. What is the meaning of orthogonal? The dot product should be 0. So these two values when multiplied with each other, so they should basically, the dot product of this P dot E should be equal to 0. Can you just confirm it? Can you confirm the dot product is 0? If this is 0, then our calculations are right, because you know that this P lies in the column space of A and this E lies in the null space of A transpose. And now if you perform the dot product, it should be 0. So this is 7 by minus 7 by 36 plus this is 10 to the 20, so 20 by 36 plus, or rather minus, so this is 13 by 36. Oh, nice. So this is 13 by this much is 13 by 36, 13 by 36 minus 13 by 36, so this is equal to 0. So do you see this picture? This projection lied on the column space, and this E lied onto this basically lies in the null space of A transpose. If you now take the product, you saw that these two are orthogonal to each other, these vectors. So what is the obvious thing? Which other vectors will be orthogonal to this E? All the vectors that belong to the column space of A. So we had this vector 1, 1, 1, 1, 2, 3. So this was our A. So any vector that belongs to this, so simple 1, 1, 1, it belongs to the column space. So 1, 1, 1, it belongs to the column space of A. So this is our A. So if you now take this and multiply it with this E, so this will also give the 0 because they're orthogonal to each other. So this is the picture that I want to remember. This is the picture that I told you. So any vector which is onto this column space of A, it will be orthogonal to this null space of A. That's why it will be orthogonal to this E, because E lies in the null space. If you see the second picture, in the second picture, what we got? The second picture, this is our second picture. If you see, this is the picture. Here we don't have this orthogonality, and you cannot basically see that. Here we just see the errors. Now we got the problem solved. We got our problem solved, and if somebody gives us a point, let's suppose somebody gives us some other point which has value 2.5. Let's suppose somebody gives us a 2.5. So here a point will be given to us, and now we'll be asked to find the value of its y coordinate. So what we'll do, we'll just drop it in the equation. So what we'll do is, we'll just, if you see the equation at hand was 2 by 3 plus 1 by 3 t is equal to y. So now somebody gave me the value of t is equal to 2.5. So the y will be equal to 2 by 3 plus 1 by 3, and this is 2.5. So I think this is nearly 1.999. Okay, the first 3 point on which we tried to find this line, that was called as training phase. Okay, now you understand this. Be here. So in the training, what we tried to do, in the training we tried to find the parameters. We found the parameters that they're called trainable parameters, or learning parameters. So we found the parameters. So what are our parameters? In our case, it was c comma d. These were our trainable parameters. And what was the value of these? So we found 2 by 3 and we found 1 by 3 was our training. And this training was done by using the 3 points whose value was 1, 1, 2, 2, and 3, 2. So these are the values, because we solved the equation ax is equal to b, and this b did not lie in the column space of A. So at that time we tried to find some x hat such that it is equal to some p. So we tried to basically solve the equation A transpose A x hat is equal to A transpose B. This basically, which I gave us the projection, and then we tested it. That is called the testing phase. So what's the testing? We had given a point, so that was 2.5, and we had to find its y coordinate, the other coordinate. So now we have these trainable parameters. We got these parameters. Sometimes this set of parameters are represented by theta. So these are our parameters, C and D. Okay, now our C and D, we tried to find this, and this value was given as 1.9. So there are two phases involved. If you see in the machine learning pipeline that I told you, that we got some data, and these were our 3 data points. So this is our training data. And now this was our test data. I took a very small example so that to show you the linear regression. So first I trained this model. So how I trained it? I used the mathematical model underneath. So I found these equations and then I solved them, and I found these projections, and this is what I gave me the trainable parameters c comma d. So I found these parameters. Then while testing, I will use those c and d. Okay, and then I'll find this 1.9. and I'll see what is the error that is it is giving. For example, the point was given 2.5 and 2.0. So now you see that the error is only 0.1. So if you see the equation, the equation that in our hand was, so we had to minimize this ax minus b. This was should be minimized. This basically even it should be 0 in the perfect case, but you saw that the things cannot be perfect. So what I'm trying to do is I'm trying to minimize this. I'm trying to basically minimize e1 square plus e2 square plus e3 square. This should be minimized, so the errors that we had, mathematically speaking. So I told you this problem can also be solved by using the optimization, by using the calculus. So how to use calculus now? In order to solve that, how to use calculus? So it's easy to solve by using calculus. How? Because the thing is, if you want to find this e1, so e1 was c plus d, I think minus 1 square, plus e2 was c plus 2d minus 2 whole square, and plus e3 was c plus 3d, basically equal to, I'm taking that minus, equal to b minus b. So here I'm taking a minus, I think it was again 2 square. So we had to minimize this equation. If somebody of you knows partial derivative, so what I'll do is, so let's suppose this is our equation, let's suppose e. So I'll take partial derivative with respect to c, partial derivative with respect to d. This is what I'll do. So I'll now get two equations. So partial derivative when I will take with respect to c. So from here I'll get this, and this will be 1. This will be basically this equation. So from this, if I take partial derivative of c, I'll get the one equation which I got from here. I don't want to solve it, you can solve it on your own. So we'll basically get these two equations. 3c plus 6d, 6d plus, and these are the equations that you will get after taking the partial derivatives. So after taking these partial derivatives of the equation that we had over here, so this is how I try to follow. I try to form a optimization problem over here, and then if I take partial derivatives, I'll get the equation 1 that I have, and equation 2 that we have right here. This is our equation 1 and this is our equation 2, and now you can solve it. So did you see the algebra gave us the tools by which we can solve this? Now you saw the training also, you saw the testing also, and now you can also find the errors. So that we'll see. And this algorithm, I wanted to see how you just did it, and we tried to do it by using the algebra, and we were able to attain the parameters c comma d, which we call as learning parameter or trainable parameters. That's c and d. That sometimes represents as theta. And we got these values, and then we saw what is the meaning of training. In the training, we use the test points, we use the train points, and to find the parameters. And in the testing phase, we try to test how much the error that we got. Okay, is it clear? Is it clear so far?
Yes, sir.
Did you saw the two pictures as well? The first picture that we saw is in the column space and null space. The other picture that we had is this picture. We got the projections and we saw these errors as well. If this is clear, then I can move to the code window and I can show you the
Yes,
real
sir.
how it is done. Can I move to the code window?
Yes, sir.
Was it clear? First tell me, was the linear regression clear? How clear was it?
Yes, sir.
Now let me go to the code window and I'll again code the same example that I have shown you so far, and I'll code the exact same example. Let me just switch to the code window and I'll see. Is this clear? Is this visible? Is the screen visible that I'm showing here?
Yes, sir.
So if you see the first, this we had 3 points. So these are the 3 points defined, for which we have this x, we have this defined this x, and we have defined this y. So these points basically are 1 comma 1, and then we have the other point 2 comma 2, and then the other point is 3 comma 2. So these are the points that we defined. This is the first point, and this is the second point, and this is the third point. And for which I'll not train. I'll not, based on this, I'll not train. So what I'll do is I'll find the a first. This is my a. Okay, this is my a, and I'm adding a bias. So in that, this a matrix that we had, this a basically is equal to 1 1 1, and then we have 2. I think it was 1 1 1 and 2 2 1 2 3, something like this. This is my a matrix. This is my a matrix that I got from the points. So if you see that, this is my a matrix. Now if you see, if I have to calculate this, so I had this matrix a transpose a x hat is equal to a transpose b. So I need to find the values of x directly. So I can find it like this: a is equal to, so I can say a transpose a inverse of a transpose into b. This is what I will find. I'll find this x parameter. This x basically was c and d. I have to find this. So that's what I have done. So if you see over here, I have said a transpose dot a. So that's this much, A transpose dot A. And then I have seen linear algebra dot inverse. Okay, and then that basically gives me this much, A transpose A inverse. This is given by this portion, if you see it over here. The first thing I'm computing is A transpose, then dot A, that is the dot product, and then I'm taking the inverse of these. This is the inverse. These three things are the inverse that I'm taking. This is the inverse. And then again, I have to take a dot product of whole of this with A transpose. That I'm doing over here. Then I'm taking the dot with Y. So the Y here basically is B, RB. This is RB. This gives me this X hat. This gives me this X hat, this X hat. Okay, now this is our X hat 0, 0. This is our Y is equal to mx plus B, or we say that Y is equal to C plus dt. That was our thing. So here we'll get the C, the intercept. We'll get the slope and the intercept. This is our slope, this is D, and this is our intercept. Okay, is it clear? Is it clear in the code? Did I did something additional? No, I just did whatever I did in the code. Is it clear in the code?
Yes, sir.
Everybody, I want at least the signatures from everybody that this is clear for everyone.
Yes, sir.
Okay, so then afterwards what I did is I took a new point. So if you see this new point, so here this new point is 2.5, and I had to predict based on this. So what I did is I'll only take this x new, whatever this point is, and dot with the intercept that the dot with the parameters that I got. So we have this x new, and I perform the dot, and it'll give the prediction of the value. So now if you again see it onto this, so these were our data points. This was our one data point first, this was our second data point, and this was our third data point. So for on these points I wanted to train, and I wanted to train on this point, on this point, on this point, and on this point. So I got the parameters. If you remember, C is equal to, and D. C was our intercept. That was I think 2 by 3, and this was our D was 1 by 2. So this is nearly 0.666 if you see it, and this is 0.5. Okay, so now from that I'll draw a line. If I'll just print those intercepts, so here you can see that the intercept B, basically in our case it was represented it represented as C, and this is our slope M, this represents D. So you saw that 0.6666 and 0.5. Based on this I can draw a line. So based on this I can draw a line. So if I draw the line, so what is the code for the line? This is the code for the line. So here I'll just draw a scatter plot with this, and then I'll, if you see it over here, so I have also drawn a line based on that. So x dot theta base, and this is the line y x predict, y predict, and then I'll fit the linear regression with this. So if you see the line now, so this is the line I got, and this is my error E1, which I said E1, and this is my error E2, and this is my error E3. If you see this is my error E3. Now I had this point 2.5. If you see this point 2.5, and this was predicted as 1.999, 1.91666 something. And you saw the training was done on these blue points. If you see this, so training was done on the blue points. Okay, so these are the points that it was trained on, and the green point was used as a testing thing. So we did testing on the prediction. We predicted for this. Okay, and then we can generalize it. So is it clear? So what was the value? If you again see it, the intercept was 0.66652, and the slope was 0.5. That we calculated by hand, and then we also ran the algorithm, and then this is the line that we fitted. Is it clear?
Yes, sir.
Yes, sir. Yes, sir.
Nice. Have you understood the concept of linear regression and how to use this if given some data points? Now you will be given more than one variable. Okay, you will not be given just one variable, you will be given more than one variables. If this is clear, then what you can do is what other people or most people that will show you how you will now implement this linear regression. So they'll import these libraries. So if you see, there is a library called sklearn. So if you see, this is the library sklearn. So in that, somebody has wrote this linear regression program. Okay, so what we'll do in that is we'll just fit this model. So we'll import this linear regression, and again the same thing is here. So this is our data, and we want to plot it. Then we'll say model is equal linear regression, and model dot fit the data and fit the labels, and then we'll calculate the intercept from the model and intercepted slope. And if you see, the values will be pretty much similar. So if you see, the values, the intercept is 0.666 that we got. This is 0.66. This is 0.449 because they use something called regularization, and this is the prediction. So are you confident that you can write this algorithm from scratch without using the libraries? That is the thing I want from you guys. So you
Yes,
should
sir.
be able to write this algorithm. Should be write this able to write, because underneath the hood, if you see, this algorithm, the second algorithm that I imported from sklearn, this sklearn, it basically uses whatever we discussed so far, and it is the optimized version of that, because they use something called as L2 regularization, L1 regular, and we'll also get into that. And I'll again again when we'll going into the develop into the machine learning algorithms, that time I'll again revisit this, but that time I won't tell you the theory. I'll just use it for the real world application. I'll just take some data set, apply this real regression. But from this discussion, what I want you guys to know is you can write all these algorithms from scratch. It's not like you'll import something and then you'll write it. And even I use the NumPy, but for you guys, what I'm telling you to try you is that you won't even use this A transpose and things. You'll write the code for transpose. You'll write the code for dot product, okay, and you will write the code for inverse. Here I just imported the NumPy, which gives me the capabilities. But as you guys are in the learning phase, at this point of time, you will not import these NumPy things, and you will not, and you'll maybe use lists, and then just compute this inverse. Write a function to compute the inverse. Write a function to compute the dot product. Okay, and then you'll be able to do that. So how many of you guys can tell me now you understand the linear regression? If you are asked any question, if you are asked any question on this linear regression, and you will be able to not just give the answer, and you will be basically telling them the underlying thing, what is going on underneath the hood. So how many of you can claim that? So I'll pause the recording here. Pause the recording. So what I told you, machine learning, most of these algorithms, you can do it by hand. Do it by hand. And then second thing is you need data. If you have this data, and you can do it by hand. But what will happen basically is it will be slow. Because for example, let's suppose you have to do the same for 1,000 data points. For each calculation, if you take 1 second, that's being optimistic. So then it will take 1,000 seconds for you guys to just compute, just train the things. That's why we in the realistic models of real world, there we have millions of data points. That's why we use computers for that. Otherwise, this machine learning, deep learning, AI, most of these algorithms, I'll say 90% or more than 90% algorithms, they were built before 19, I'll say 60s. Okay, but what were the two problems? The main two problems were, the first problem was data was very less. We had very less data. This data was not present. Maybe we had data, but it was not at that large scale. And the second thing was we had this very less compute power. Both of these things we had less data, and we had less compute power. And now what made this AI ML sort of boom in this area, in this era of ours? So the first thing is we have a lot of data now. And again, we have a lot of compute power. Do you know that Sam Altman made a comment about India? He made a comment about India that India won't be able to make a thing like ChatGPT. How many of you know this? The owner, the founder of OpenAI, not even the founders, he was one of the founding members. His name is Sam Altman. So
Yeah.
when he
इसको
came to
file
India,
किया हुआ था.
so he made a comment on this. He made you won't be able to make ChatGPT. It was not to demean that you are not good engineers. So he said because it uses a lot of compute power. Maybe you have data as well, but compute power, being a underdeveloped country, and you are still developing, you cannot give, let's suppose, 20% of your energy to only the training of one model. So that developed countries can do. Now if you see geopolitically, China is now making these having a lot of compute power in this, and there is a sort of geopolitical war going on this compute. So whoever has the compute power, he's winning the game. That's where quantum computers can come in, where I research in that area, quantum computers. So we try to find alternative ways of this faster computation. That's the whole game of this. If you want to be better, maybe you have all the algorithms, you have access to the algorithms, you have the data as well. But where to get this compute from? That's the point. That's the point of research right now I am conducting. So how to make the algorithms faster. Is it clear?
Yes, sir.
So now at least you. So the conclusion here I want to draw is that you can do the machine learning by using your pen and paper, but for that you'll have to have a lot of patience to do this. And I know people who have been doing it with the hands, and I have met some of these people in I think in their career when they were given the data and they had to fit these lines and fit these things, but they have to just compute it by hand. Now you have computers and you can use the computing power of that. So here we'll end the discussion on the linear regression. Okay, now we'll move on to the other things. So can I end the discussion here?
Yes, sir.